Hello, John.
Hello, Jack.
And
Rima. Hi, Manu. How are you?
Hi, guys.
Can you guys hear me?
Yeah.
Yes.
Good. Good.
You,
Hello.
you got this very beautiful landscape.
Oh yeah.
Behind you.
And it's moving. The water is moving.
Oh, that's even dynamic. I did not notice that. I saw the foggy air there. I did not notice the water is moving. Well, that part we could certainly learn from Manu, see how your water is moving. Anna just slacked you.
Oh.
Anyway, I think Jack, Dave mentioned he will not be here. So if you could help facilitate this, my memory was Manu kindly agreed to share his insights on teleconnection, hydroclimate dynamics.
Yeah, that's great. Can you give him the privilege to share slide if you have any slide, Manu?
Yes. Yeah, Manu should be able to share the slides.
Okay.
Let me try.
Yeah.
Okay,
Yeah.
you can see it.
Yeah.
All
you
right.
can see. Yeah.
Okay, so this is not a polished talk. It's basically to expose a couple of ideas and then, we can be discussing. So tell me when I should start or if we are waiting for people or what to do?
I think you can get started.
Okay.
We are
Yeah.
recording anyway, so for those who are not able to join, they can watch the video later.
Okay, that sounds great. And please feel free to stop me anytime, don't wait till the end, basically. So in line with the last meeting that we had, and also what we had in the proposal, etc., I thought that I will try to expose this idea that's listed on this slide, which is, can we estimate national, international, socioeconomic impacts of the potential climate-induced failure of aging US dams? I mean, we could do dams anywhere, but we are here, and here we can get data. So that's kind of the idea. And the subtext here is that I'm going to bring in the climate teleconnections and the supply chain economic teleconnections as well. So there's teleconnections on both sides of this kind of story. And what you're seeing here is actually a dam, which is a tailings dam, which holds mining waste in Brazil that was captured in real-time failure 3 years ago. And it had obviously significant impacts on the company that owned it, a multinational company, but also reverberating through the mining industry in terms of commodities prices globally and production. The mining area is actually an interesting one because the US has had that as a major economic piece in the past. And what is left of that in the US is just waste piles. And so there's quite a bit of risk associated with what happens when they fail because there's no one really monitoring them. But mining is for the renewable energy economy and for other areas, for example, the growth of China, a very, very critical piece globally. And so what comes with mining is a bunch of these tailing dams. So globally, that's a big issue. In the US, it is an issue with a slightly different flavor. But most of the time, I'm going to talk about regular dams on rivers rather than tailing dams, although I think it may be worth considering both of them. So these are the two main points that I'll try to develop. The first one is that the US has a very large portfolio of dams. These dams are now old and they're not being maintained very well. In fact, while there are organizations in the US that are responsible for dam safety, the typical number of people working for these organizations is small, and the number of dams is large. So for example, in a state which has 5,000 or 6,000 dams that need to be inspected on a regular basis, you may only have 3 or 4 people who are responsible for that. So the question is, what happens if one of these aging dams fails? What typically happens is that the flood wave generated by that is going to be larger than any natural flood that we are considering at that location, depending on the duration and severity of the failure and how quickly it fails and the mechanisms and so forth. But the issue I'm interested in is, in part, what are the immediate and direct impacts of that failure, which are obvious, is the flood wave, but what are the long-term and teleconnected impacts? And can these be predicted to inform portfolio risk management and investment in the remediation or removal of these dams? To give you a sense of this, the US Congress actually decided to put together $3 billion to fix these dams. And I was testifying before the Congressional Committee. And it was really interesting because I was trying to point out what the scale of the problem was. And these guys said, oh, we weren't aware of this when we passed this bill. And I wasn't aware of the bill being passed. So my reaction was, well, it's good that you guys are putting up $3 billion. That's at least a start. They said, no, it's $3 billion over the next 30 years. And I'll give you some numbers on what the cost of some of these dam failures has been. So it's not even relevant what they are doing. So the second point I want to make is that we know that there's climate change and there's an increase in the frequency and severity of both droughts and floods. What is not as appreciated is that most of these extremes are not random, even today. They are spatially correlated over the globe, and they are teleconnected in terms of the causal factors that drive the occurrence of those events. So what I mean by that is that in a season in which you get a high probability of major floods, for example, in the northeastern United States, it's quite likely that Western Europe is going to experience exactly the same thing because the mechanism that launched that is the same mechanism. And correspondingly, a season in which, for example, China is experiencing major flooding is quite likely that the Western United States is going to experience significant droughts at the same time. So the question, the way these things couple is that if there is a high propensity of extremes that could lead to dam failure over diverse regions, and that leads to supply chain impacts for very specific supply chains, then we could be looking at a fairly significant global economic risk associated with certain commodities. And then there's also the question of what happens when you compound those risks with supply chain risks, for example, due to the pandemic, for example. So those are the kind of things that I'll be trying to give you a storyline on. So dam failures, just in the US, we had 2 last year in Michigan. And those are the top 2 pictures that you're looking at. And then the bottom left is Oroville, which at 700 meters is the tallest dam in the United States in California. And that nearly failed in 2017. And just to give you a context, just the reconstruction cost of the spillway on that particular dam, which did not actually completely fail, just the spillway failed, has already crossed $1.25 billion. So the government putting up $3 billion to repair things is really not in scope of what they need to be doing with regard to these things. So that's that. And then to give you a sense of how many of these dams are there and where they are, we have this picture. And the dams that are in the reddish orangish color are listed as high hazard dams. The ones in the blue color are listed as significant hazard dams, and the ones in the gray color are smaller failure dams. Black ones are the smaller impact dams, basically. So a lot of these, about 2,000 of them are currently listed as in unsatisfactory condition. The ones that I had on the previous slide that actually failed were not listed in unsatisfactory condition. So that's, kind of interesting as to what goes on. You can see these are all over the country. And high hazard just means that there will be loss of life if the dam fails. It does not reflect the economic impacts. Significant means that it could have significant economic impacts, but not loss of life. And what significant means in terms of economic impacts is basically a measure of, is not basically priced in terms of, $1 billion impact or anything like that. And certainly they have not looked at teleconnected impacts associated with these. On average, we've had 10 dam failures, but this has been going up per year, but this has been going up to around 24. Luckily, most of these are small dams, and so the impacts have not been significant, but the state of repair or the condition of even some of the larger dams in the West is now questionable. The ones that I would be most concerned about at the moment would be dams in the Ohio River Basin, the Mississippi, and dams in Texas in the Houston, Dallas areas. But certainly dams in California and along the West Coast as well. So this is to show you, some sense of how old these are. So you can see that this was done in 2016. And it's in a paper that we put out it came out in 2017. Very few dams are young. A lot of the dams are over 100 years old. The median age of dams is around 60 some years now. And the expected physical life under decent maintenance of these dams was supposed to be around 50 to 75 years. So that's why there's a concern. The subtext on this is that before I started investigating this, my mindset was the Army Corps of Engineers, the Bureau of Reclamation, etc., own most of these dams and they must be taking care of them. And it turns out that out of the 90,000 dams that we have, roughly 4,500 are owned by federal agencies. The rest are not owned by the federal government. The 50,000 of them are privately owned, and a lot of them are owned by cities and municipalities who really do not have the budget to keep maintaining these dams. So in the insurance industry, they have a very interesting way of dealing with this. As explained to me by a gentleman from Munich Re, if they were to actually price the premium on these dams based on expected losses and reconstruction costs of the dams, the municipalities or the state agencies would not be able to pay for, or the private owners of the dams would not be able to pay the premium. So what's typically being done is that there is a maximum limit put on what the insurance company will cover. And then the premium is calculated on that basis, such that there's affordability for the premium on the part of the entity that is buying the insurance, so that they can say that, yep, our dam is insured. And then at the same time, there is a limit to what the insurance company will have a liability for. So both people are happy. And the understanding is that if the dam did indeed fail, well, there will be a presidential declaration, because there always is, and the federal government will bail them out. So that's where we are as a country in terms of managing this risk. So we've been thinking about how one should approach this. And clearly, one needs to understand the dynamics of failure, and we'll talk a little bit about those. But we need to understand what the impacts would be. And so on this slide, I have listed direct infrastructure damage, plus loss of services that would happen immediately, plus loss of life. But then there are many indirect impacts, because if this is a dam and canal system and the dam fails and is not replaced, then there's a variety of things that would basically lose those services down the road, and those are listed in that next column. And that's where I think the interesting impacts come into the national economy. And these are not impacts that would be local, because the transportation sector would have impacts, both in terms of navigation, for example, on the Mississippi River, or in terms of major highways, bridges failing in the process. And then a lot of the things that are produced using the water from these places would, of course, translate into the supply chains and the economies. And none of that is currently being priced into these things. Likelihood of failure analysis. The predominant mechanism of failure is in 37% of the cases is overtopping because of a high amount of water coming into the dam and the inability of the dam to contain it. This was the case for Oroville. It was blamed on climate change by my colleagues at Stanford, which is interesting because the New York Times very quickly picked up on that and published that. And I wrote an op-ed, which the New York Times did not want to run, which basically pointed out that the flow over the spillway was only 5% of the design flow, and the spillway failed, and it was poor maintenance. It had nothing to do with climate change. In fact, the reservoir was full, but that was in part because of the operating rules and in part because it was actually quite wet, but not a single event. It was just a very wet January that year overall. And they could have managed it differently. So anyway, this is one of the main mechanisms of failure. The other mechanisms of failure, for example, in California, could be earthquake related. And about half of the dams have had reconstruction to manage earthquake risk there. In terms of overtopping, obviously, the big issue here is a lot of water coming in. So that's the climate connection. But there is also the issue that a lot of these dams, since they are old, they have had a lot of sediment build up behind them. So the effective capacity to store water has diminished. So the design risk is not the actual risk today. And then, we've developed ways by which we have done some analyses, for example, in the Cumberland and Ohio River basins, looking at how can we estimate immediate and local damages. And so this slide basically is an illustration of the kind of information that you can bring in, but it is indeed quite crude. And the task of looking at how one could analyze this for 90,000 dams across the country is non-trivial. So we've been trying to develop or think about ways by which we could do strategic sampling-based design and then use machine learning to project it onto the rest of the place. But in terms of our project with iGuide here, the thing that I was thinking with the presentation last time by Tom Hurtel and the group was that perhaps we could have a very different approach to this by considering that, instead of focusing on when will a dam fail or what will happen given its fragility and climate aspects, basically do a mapping of what is the value of these dams to the national economy by looking at all the teleconnections, since they have a model that could facilitate looking at some of these aspects. So that's that. And then, just very quickly, there's a bunch of dams in this Cumberland River Basin that a lot of data has been collected on by the Army Corps of Engineers. So it was a quick target for us to look at. And we did a bunch of analyses, climate oriented and hydrologically oriented, and then in terms of the impacts. And basically what comes out is that even though all of those dams are rated as high hazard by FEMA and by Army Corps, they don't have a detailed analysis of the economic and population impacts. And once you do that, you can see that those are very, very diverse. And of course, these are just local impacts. These are not teleconnections, as I was talking about earlier. So, things like that can be done. So that's the first point that I wanted to drive at is that nationally, this could be important to try to understand. And then some of the impacts that would emerge from flooding actually will come out in this piece that I'm talking about next, which is on the role of climate, the nature of climate extremes, some of the trends and their impacts. So these are some slides from a talk that I gave in 2009 at Tufts. where I was thinking about global impacts of water, namely flooding and climate and through supply chains. So it was very interesting when Jack and others were talking about teleconnections, because this is what I was trying to convince the hydrology community of at that point, and frankly got nowhere. Most of the hydrologists are interested just in watershed scale processes, but not in things like this. So they weren't particularly responsive to that. But to give you some examples, this is 2011, and I had some undergrad student interns while this event was developing in the Mississippi River flooding, monitor all the news media so that we could try to understand what actually happens in a flood like that. And this is a flood which had a duration of around 130 days continuously. So somewhere or the other over the main trunk of the Mississippi, there was continuous state of flooding. And that one of the primary impacts of that was navigation on the Mississippi was basically shut down. And some of the impacts from that were that essentially goods that were produced in the upper Mississippi, but were sent to the port of New Orleans, were never making it there. And the reverse direction, oil that was brought into the upper Midwest from the refineries in New Orleans was not getting there. So things like milk, things like anything that was dependent on the prices of gasoline basically appreciated in price quite quickly. Other things that were going on that were interesting were that farmers were reapplying fertilizer and seed in between these flooding events as they were going on. So they were in the early stages of the flooding, they were doing that. And so there was quite a bit of increase and gain for Monsanto in that process. So there were winners and losers is basically the idea. And there were other things that happened where many of the companies that were operating shipping were both directions were actually out of Houston and New Orleans. And because of the loss of revenue and their inadequate insurance from loss of business use because of flooding, they ended up in dire straits. And then by the end of the period, a lot of the farmers and other producers in the Midwest decided to redo their contracts. So they were shipping through the Great Lakes rather than through Mississippi for future contracts. This led to the bankruptcy of several of these companies. So I present this more as an illustration of how these impacts become teleconnected rather than just as a story in itself. We talked about Thailand before, so we published on this as well. And I think most people probably know the story. There were basically 5 hurricanes or typhoon landfalls, which led to flooding in Thailand, again, over a 100-day period continuously. And Bangkok, which is where much of the manufacturing for things that actually come out of Thailand was placed, received the brunt of this flooding. A fun story here is that when this was going on, I got a call from ABC News National asking me to be on the evening news to discuss this. And my reaction was, sure, would love to. And then at 3 o'clock, the guy wanted to do a preview of what I would say. So he asked me, why the flooding was happening. And I explained what was going on. And he said, no, that's not the story. The story is that there are a series of dams here that were mismanaged by the government. And that's why things are flooding. And I was going, I'm sorry, that's not it, because there's no way, there was nowhere for these guys to release the water from the sequence of events that happened. So the guy abruptly cut me off, and I was not on the news. In fact, they got a guy from the UN to come and say exactly what they wanted, which tells you a little bit about the objectivity of reporting on the media nowadays. But we've analyzed this quite extensively, and indeed, the situation is that there is a limited capacity to do something about the kind of event that happened here. So the supply chain losses, not the physical direct losses, but the supply chain losses were priced at around 5 billion. And the automotive supply chain time to recovery, depending on the company, was 30 to 174 days. And this is global. This is not local. So for example, for Toyota and Honda, these were bigger impacts than what happened when the tsunami hit Japan. And there were factory shutdowns in America and North America and in Japan, North America being US, Mexico, and Canada. And these were due to the lack of parts for assembly, and the parts were what would have come out of Thailand. This also reflects the just-in-time inventory model that most industrial supply chains follow nowadays, because they want to minimize inventory to reduce overall costs for things that are in storage. But this was the impact associated with it. Similarly, the electronic story is actually more interesting associated with this, because it turned out that Western Digital and Toshiba and Seagate were the three main manufacturers of hard disks that go in laptops globally. And all three of them had manufacturing facilities in Bangkok. Western Digital and Toshiba were basically completely wiped out in terms of production. Seagate, I had discussions with all of these people prior to and post that event. And Seagate shared quite a bit of information with us, because they had anticipated that in Southeast China, as well as in Thailand, which were the main areas where electronics are getting manufactured, there's some in Malaysia and Singapore as well. These were quite vulnerable to flooding. So Seagate had diversified their manufacturing facilities so they could limit their exposure. That was not the case for Western Digital and Toshiba. So Seagate actually made out very well in this situation, because what happened is that the price of hard disks went up spectacularly. And the laptop manufacturers, Dell and others, they curtailed production because they didn't want to pay the high prices. So an interesting side effect of that was that all of a sudden, the RAM memory that was used in laptops was in oversupply. And so RAM prices crashed, and Micron, which is a US producer of RAM based in Idaho, they actually had a very large loan they had taken to modernize their manufacturing facility. And that was coming due at right about that time. And since the prices of RAM collapsed, their revenue collapsed, and they had to file for a bankruptcy. The reason this becomes interesting is that for Western Digital and Toshiba, their loss of business use insurance kicked in. So they got some coverage from that, and they didn't end up in as dire a state as they would have otherwise. But Micron couldn't claim that because they had no operations in Bangkok. So they had no insurance cover that could cover something like that. Luckily, Micron survived, but that shows you the nature of the impact that can happen in a teleconnection sort of sense, where a company that actually had no primary exposure to the event is the one that is getting the most effect. So, we've looked at this for other industries and tried to understand what kind of risks there are. And so I'm going to show you some analyses associated with those. So we have looked at different sectors, mining being one of the more interesting ones, and then agriculture, of course, is another one. But let's talk about mining, because what I have plotted here on the y-axis is the percentage of global production that was at risk from a specific type of climate extreme event. In this case, it's a wet or a dry event that has a 10-year return period, which would lead to disruption of manufacturing at the principal locations that are manufacturing the particular thing. So in terms of crops, we've done this for different crops. In terms of mining, we have what I'm showing you here is copper and gold, but we have done it for other mining commodities as well. And then we have done this for urban populations as well. So what's interesting is that this is based on reanalysis climate data going back to 1900. And we see several years here in which, for example, for copper, 35% of the global production could have been disrupted because of extreme climate events, hydroclimatic events that occurred at the locations where that manufacturing was actually located. So that's quite interesting, because a disruption of that scale for a commodity which is non-perishable like copper, you think would not have a significant effect. But based on what we have seen with, for example, the dam failures that I showed you that video of right in the beginning, at least in the short term, these can lead to fairly significant valuation changes in the stock market, as well as commodity price changes. So it's a fairly significant impacts that go through and reverberate through other supply chains. For mining, we can look at an example here, and you can see the interesting thing about mining is that it's concentrated in a few countries. And most of the mining products today go to China for manufacturing. And then from China, the manufactured goods go to basically everywhere, is the idea. So we looked at a variety of mining companies, and I'm showing you an example for 2 of them. These are in the top 5 mining companies globally. And this is for copper. And it's basically localizing to a company the kind of picture I was showing you earlier. So the top part of the picture is the global mining locations for Rio Tinto and for BHP Billiton. And then the bottom picture is the potential occurrence at each of those mines that these guys own of a 10-year return period, 30-day rainfall event. So basically the idea is that the reason we are looking at a 30-day rainfall is that if we get extreme rainfall events, which are of long duration, that's where the mining activity is more likely to get stopped, because many of their tailings dams and other dams will be filled, and there's also other disruptions that happen. And so that's on the left, and on the right is a 10-year drought. So if you look at the bottom line here, that what's interesting is that Rio Tinto has 40 mining locations for copper. 36 of them in one of those years actually experienced this extreme event, and 32 in another year. So that could, if they had disruptions at all of those locations in those years, and not all of these mining sites had operations in those years, that could have been fairly significant. And what you see is that there is a trend in this, but there's also significant decadal variability. Similarly for BHP, out of their 38 mines, 24 of them experienced this in the worst year. Now the probability, if these things were just random, the probability with which this could happen for to this extent for these companies is 10 to the minus 19, basically 0. So essentially what it shows is that the way the climate system works, these extreme events can actually be quite clustered in time and demonstrate quite a bit of spatial structure across space. So this graphic makes that point, but I guess I've made that. So I'll just show you some more illustrations of this. This is looking at gridded pixels of half a degree, looking back in time across different climate zones, all grids, gridded data across minus 60 to 60 north, and in the tropics and in the subtropics and extratropics. And what you see is that the number of grids that show an exceedance of the 95th percentile of annual maximum rainfall in the same year is spectacularly larger than the average in all zones of the Earth. And typically these things are happening in years where there is some specific type of El Nino or La Nina activity in the tropical Pacific. And just to show you another way of conveying that in terms of the causal or spatial structure, this is something that I had a high school student who competed for the Intel Science Talent competition and finally placed second or third, I think, do in the year 2000. So it's 20 years ago. And what she did is she looked at each one of these states going from north to south, Washington to Southern California, and identified the 10 largest floods, the years with the 10 largest floods and the years with the 10 smallest floods. These all happen in the winter. So she looks at the winter sea surface temperature, and the average sea surface temperature picture for the 10 largest floods is plotted on the left. And for the years in which there were 10 smallest floods occurs is plotted on the right. And what you can see is that if you look diagonally, the top left picture is quite similar to the bottom right picture, and the top right picture is quite similar to the bottom left picture, which basically speaks to the fact that the way this system works is that we have very organized moisture transport that emerges such that when the Eastern tropical Pacific is warm, we get a high degree of flooding in Southern California. And when it is when the central and eastern part of the Pacific is anomalously cold, you get strong flooding in the Washington area. So, one way of saying this is that there's basically a hose that you can locate in the Pacific, and the hose sprays in Washington rather than California in one condition, and in the opposite condition, the hose sprays Southern California, but not Washington. So, and we can then translate that into the probability of floods. But what it says is also that you're going to get strong spatial correlation and clustering in the flood process in those areas. And we have looked at this for the top 10 floods in different regions in the US as to where the moisture comes from. And this is averaged across events that have happened in many different years. So for example, the top 10 years here could be 1939, 1945, 1985, 2010, etc. They're different for each location, obviously, but they are averaged across all those events. And what you see is that irrespective of which geography you look at in the US, for the top 10 events, there's very coherent, on average, moisture transport that brings things in. So contrary to what we have believed as hydrologists traditionally, we think that there is random strong convection events that happen, for example, in the Midwest, which is where I am showing you this picture, and that leads to the big flooding. Unfortunately, that's not the case. Most of the big floods actually correspond to large-scale moisture transport coming out of the equatorial and tropical oceans. And we have translated that into predictive schemes using machine learning. So this is a particular machine learning scheme applied to sea surface temperature data in the Pacific tropical oceans. And it identifies that there are 5 hidden states associated with the temporal dynamics of the sea surface temperature. So we identify those, and those are shown here. And you can see that these are similar to the picture I was showing you for the floods from Washington to Southern California. And then what we can do is that we can look at whether these hidden states are informative of what happens in terms of extreme precipitation on the wet side or on the dry side in different parts of the world. So just to be very clear, the only data we have analyzed is sea surface temperatures in the tropical Pacific. And once we have a classification of those, we simply look X months into the future and say what is happening X months in the future in terms of extreme precipitation around the world. So this is April looking at May. So the hidden state is the hidden state of April sea surface temperatures in the Pacific. And then we are looking at May precipitation anywhere in the world. And the color scheme is that if it's red, dark red, then in that location, we are getting the 99th percentile of rainfall in the month of May. And if it is the dark blue color, it's below the first percentile. So we are getting the two extremes. So you can see that depending on whether you are in state 1, 2, 3, 4, or 5, which had specific sea surface temperature patterns, we get very different means and standard deviations for precipitation 1 month into the future. And a lot of them are extremes, and they're covering large spatial geographies. So once we can predict something like this, then we can go and look at what kind of teleconnected impacts would be for things that are produced in those regions that have global relevance. And then this is the same picture, except now we are looking at a prediction for May, looking at the hidden states from the previous year's August, so 9 months into the future. So we find that we have quite a bit of predictability, and we can also look at this in terms of if you continuously predicted every single year for the last 70 years using data from the previous year as to what happens, do we have skill? And the answer is yes. This is a paper that's in review. All the other things that I was showing you are things that have already been published. So no one stopped me, so I'm done. And maybe I'm most interested in what people thought in terms of what I presented and what would be what would be the interest in following this up?
Yes, thank you so very much. That's great, fantastic talk, very inspiring. And we'll have some time for questions. I will get started with the questions. So those are very important issues. You gave some examples. My question to you is that, do you have a integrated framework to address those kind of issues? And
Yeah.
if so, what the framework look like?
Yeah, so in general, the way I've been approaching it is in the spirit of Bayesian networks or causal networks. So so the idea basically is that there is a cause and then there is an effect. And so at that level, we are looking at statistical or machine learning models that allow me to predict conditional distributions associated with cause and effect. And these can be networks rather than just one cause and one effect. Then within the cause and within the effect, the spatial geometry is represented by geographical or topological networks. And so the idea is that when I look at topological networks, in the case of climate, these could be actually network relationships across grids that have been extracted from the data, or they could be reduced dimensions, for example, using principal components analysis or hidden Markov models. And then once we look at, or if I'm looking at commodities, then it is actually the topology of the supply chain networks. But in that case, I'm interested in seeing how an entire network responds to shocks. And the shocks may be in one location, or the shocks may be supplied so that they are representing a spatial structure on the network.
Yeah, that's good to know. That's a kind of, in my mind, is kind of methodology, how to analyze the cause and the effects.
Yeah.
And I was thinking about more unified conceptual framework.
Right. So, yeah, I mean, I understood that. I think in my mind, the conceptual framework here is one of networks. And it's one of stochastic networks, which is why I was getting into the methodology of how we are operating it.
Right. Definitely, they are networks. And the, like in the teleconnections work that we have been doing and others have been doing, we have a framework actually have 5 major components. One is system, the location, like where the location was the dam, for example, and then or where the disaster occurred, and then even for the system, we have different systems. With sending system could be the location of the dam, which send water, a lot of water to other places. And the receiving system or spillover system. And then you have the connection is through the flows. In this case, maybe the flow of water, maybe too much water. And then you have the agent, the facility, the entity that facilitate the flows could be the company, the shipping company or the manufacturing company for that. And then you have the causes and the effects and social, economic, and the environment, and so on and so forth. So that really help us to unify a lot of kind of distant interactions, from migration to trade to almost everything. You know, we have not found an issue that had not been suitable for this kind of framework.
No, Jack, I appreciate that. I think you're right. In terms of conceptually describing it, one would do it exactly as you're saying. My brain works more mathematically than it does with words. And so the way I've thought about it is, in a hierarchical structure, you cannot model everything at the same level of detail. So basically, I think in terms of a hierarchical structure of networks, then within each node in the network, there may be a much more detailed model. And so you have an aggregation or disaggregation process, and many of those working at different levels. So obviously, at a particular level, it may be that an agent-based model is needed to resolve what is going on there. And at another level, it's going to be a spatially discrete model that is working in a continuum, and at another it'll be networks. But in terms of organizing my thinking, I find it very useful to think in terms of hierarchies of networks.
Yeah, so actually we also use networks to analyze some of the issues. Recently is a paper in Nature Sustainability led by my student actually analyzed the supply of water services, water ecosystem services from 2000, more than 2000 watersheds to more than 300 cities. So that's kind of a network analysis too. And so in this case, although it's not disaster, it's kind of a service. You know, there
Sure.
actually a lot of water come from dams, and some from the forest watershed, but also there's from dams. So I'd be happy to send you the.
Yeah, I would love to see that and learn from it.
Oh, actually, sure. When just the send us the
Sure,
chat in the chat.
I've picked it up. Okay.
Okay, so
Good.
that's great. Thank you, Sean. So that's, I think, something that I think we have a lot of common issues to address. And actually, you talk about your frustration with the media. Actually, so far we have been very lucky. Time Magazine has reported telecovering twice, at least, according to my memory. And so even the Nobel Prize Summit featured the telecovering.
That's
So
great.
maybe we can work together, maybe explore the possibility
Sure.
of how to, expand the work that you have been doing. I think the issues are hugely important. So I will stop here, and I know you might have hands on up, and if we have more time, we can talk more. So,
Great.
Iman.
Thank you very much. I have a lot of questions. This was very
Sure.
talk. I really enjoyed for every slide of the discussions. Thank you. So I'm not expert on this. I have a couple of friends of mine at Purdue working on the flood issues and the climate change and the economic valuation of that. So just one clarification question is when you are talking about dams, are you talking also about the check dams? Is it included, or is it different thing?
No, so typically we are talking about dams that are taller than 15 meters.
Okay, so good.
So the check dams probably are not an issue in this. Yeah.
Okay, good. That's great. Also about the relationship that you are estimating. Are you estimating the likelihood of the happening of the event, or also you are looking at the severity of that? Because the flood, I mean, the length of the precipitation, the heavy precipitation.
Yeah.
Yep.
So let me describe, I didn't want to get into the full detail, but let me describe a bit of it because you asked.
So before going to the answer, I have my last question. So
Okay, sure.
Decide how to allocate your time. And have you looked at any economic database on the damage from flooding and all of these extreme events?
Okay.
Thank you.
Yeah. So the specific modeling that we do starts with a climate model. You generate rainfall. You now have to run it through the hydrology. And so what many people do is they will just calculate like a 100-year event and run that. But in the context of dam failure, that's not useful because you want to know what the storage in the dam was as well at the time that the water came in. And so I have to do it as a continuous simulation. And yes, I can choose segments of the data because a lot of the data is not going to give me an event. So why am I bothering with it? But I do need a continuous simulation to do that. And then when the failure occurs, we compute the volume of water that is released. So that's a severity indicator. And then the probability is computed at the moment primarily based on the probability of overtopping. But one of my colleagues who has been working with me, who's a structural engineer, he has approaches to calculate the age-related fragility with which the dam would fail. So a dam that is old and not well maintained is more likely to fail than one that is in good shape. The trouble is we have no data on fragility, so we can't do anything with that. Then the second thing that you were asking was about, is there a database of economic damages? Unfortunately, no. What we have is FEMA puts together a database called HAZAS, and it's a crude approach. Probably some people who are big into this will be mad at me for saying that, but it is a crude approach which says, if the water level around a building rises by 5 feet, my damage is $10, that kind of thing. And it doesn't know about the specificity of what that building contains or anything like that. So what people do is typically they will use, in the absence of anything else, they will use those kind of numbers. And they do not, there's now some estimates which provide some uncertainty ranges around that and so on, but it's pretty crude.
Courtney, I think. Feel free to go ahead.
Hi, thanks. Yeah, this is so great. I have like 10 questions and we have like 8 minutes, so we won't get to all of them. And maybe we can talk more because I'm really interested in the news media analysis potential here. I've done some news media analysis very, very painstakingly. And I think that there are lots of tools through iGuide that we can use to get at. And I'm more interested in capturing sort of awareness and risk perceptions related to this that might actually be related to the adaptive capacity and emergency response capacity, but that we can save for another day. What I'm curious about is 2 questions, I guess I'll focus on. One is the role of drought in the infrastructural weakness. We're seeing in the Western United States, we have so much drought. Does that present an additional weakening factor, like for erosion or some other, drying out, some other, hydrological problems related to drought? And then does the speed at which you go from drought to flood conditions, does that influence the dam's infrastructural capacities? So might there be a real temporal dynamic to this extremes, the both ends of the extremes? And that's question 1. And then I may have missed it, but it seems like there'd be something important about interbasin water transfers and whether you can turn water off or on, between different river basins in advance of a potential crisis or in the immediate response to. And then, of course, that affects everything from water rights, especially in prior appropriation states. And so all of these sort of legal ramifications. And I'm also interested in the timing of the demand and the fact that a dam failure in sometime in the winter when water's not being used is going to reduce the ability to use that water when it's actually needed later on because it will have flown all the way by. So some of my questions. Thank you.
Those are really insightful questions. And they have been looked into a little bit by people who focus on one dam at a time, but not in general. We don't have an understanding of those. So first answer, does the cycling of drought and flood impact the fragility of the dams? Yes. If they are earth dams, totally. That's one of the issues. If they are tailing dams for mine waste, that would be my number 1 concern for failure. And there's a lot of abandoned tailing dams in California and Arizona and Nevada, for example. So that would be an issue. The second one that you had was on the transbasin diversion story. So the example I would use there is Oroville, the one that nearly failed. Around half of the water that is stored in Oroville goes to Southern California. So if Oroville had actually failed, Southern California would be basically dust, right, at this point. And the fact that they allowed a primary source. So the thing is that in 2004, there was a determination that the spillway was damaged and it should be fixed. And they did not fix it. So actually, the city of Oroville is currently suing the state of California because Obama sent them money to fix it and they use the money for something else. So they're suing the state of California for essentially creating this where 200,000 people had to be evacuated and all kinds of other things happened. But you're right. So if this is a good example where there's a transbasin diversion with significant impacts, but the total number of transbasin diversions that we have in the US is luckily not that significant, but it would be a concern. And you had the thing about media. I think that's super interesting. I would love to work with you on that. I end up dealing with the media a lot because of being in New York, not because I do anything interesting, but they catch you because you're here. And I would say it's a really mixed bag. There's been a lot of reporters who are super good. The Guardian comes to mind, National Geographic comes to mind, but when it comes to climate change specifically, the media has one story to tell. They've latched onto it, and that one is a hard one. And the example I gave about the Thailand one, that really surprised me. I've not had that kind of a thing other than that.
Right, Andres?
Yeah, well, I second what people have said, Manu. It's an outstanding work. It's very insightful, and it has brought lots of questions as well. I have also many questions that I would like to ask you, but given time, I would like to ask one specifically that I caught my attention, and it's, you have a box and arrow where you have one of the causes of the dam failure is the water capacity, carrying capacity, the storage capacity, and that's also affected by sedimentation. And then you have land use, an arrow pointing into sedimentation. I would like to know what type of analysis you do to input land use into.
Yeah, we haven't so far, Andres, we recognize that. And what we are stuck with is that if you want to do the analysis for a national scale or even a regional scale, we are forced to use textbook numbers.
So it's like a lookup table and then boom.
Yeah, that's what we have done so far. My attempts to get funded for that work have not led anywhere. The last one, interestingly, was to an NSF program, and it failed. And I'm used to it, so I'm not bothered. But then when I got the summaries of the panel, I was shocked. The panel recommended funding, and the program manager chose not to fund, which has never happened. And I've been on panels so many times, and they tell you, I don't want to fund this, so why don't you scuttle it? So I talked to the program manager, and she said, oh, you're trying to talk about national planning. We don't do anything nationally. I just don't think your work will be useful. So I was going, great, thanks, lady.
So terrible. But you
surprising.
Surprise. You never know what's going to happen in the end with this. It's always frustrating.
Yeah.
But you have, for example, you give more weight to things like urbanization or what?
No, look, so far what we have focused on, is essentially building the framework, which is what Jack was asking the question for how to address this specific question rather than the overall thing that I'm talking about today. And so what we have done is when the first time we couldn't get funded, I thought, let's just go ahead and do one, the Ohio River Basin, because why not, right? So you do that because we know for NSF, you have to show them that you've actually done the project before they will fund you. So we did that, and then we get this result where the panel is happy with you and this person kills it anyway. So we've been waiting to actually this is basically, a failure to launch story rather than a story where we have done extensive work and I can tell you good answers for it.
Well, something interesting there to work in. Yeah. Thank you, Manu.
Yeah, that's great. Our time is up. So thank you so much for your excellent presentation and wonderful discussion, everyone. And I know there are more questions, but you can email Manu, or we can have more discussion other times. And
please do. Yeah. And thanks, Jack, for organizing this too.
I think Shawad has a question. A quick question.
Yeah, I don't want to get people dragged here, but just want to quickly say, super interesting. Manu, thanks so much. I was asking a question in my mind, which is how to we potentially move forward with this set of ideas, I think has huge potential. I was surprised NSF was not convinced to give you support, which I think they made a huge mistake. So in my mind, as you know much more better, for instance, USGS has this gauges data, right, across the country, 2.7 million, measurements all the time about the sort of river water levels. So I was thinking along the line, could we conduct national scale analysis with this telecoupling, teleconnection in mind to see, using your overtopping analysis, because we have data, if I understand correctly, and to see how this cascading potentially failures could be related to each other and amplify sort of the bad impact at a larger scale.
Yeah, I think we can definitely do that. That's not an issue, especially if we restrict ourselves to historical climate and don't get caught up with trying to produce data for unrealistic future climate scenarios that people are putting out. Then I think we can definitely do this.
Yeah, because at this larger scale, using this notion of telecoupling and teleconnection, to me, I would say it's novel, right? To perform this larger scale assessment and give this substantiated in terms of how big is this alarm and informing not only science but policy, right? Possibly going forward. We have data at national scale, and you have the overtopping analysis already at some smaller levels. So it seems to be tangible.
Yeah, and we have a model which can be run in simulation or optimization mode, which has all the larger dams and all the canals in the US and all the river systems mathematically defined already. So to do this will not be that hard. It's just finding the time and people to run it in a way.
Yeah, I think iGuide seems to be the right forum to get help and then pull this together. And then once we've done this, and we could sort of go to the next level, say, hey, how the socio-environmental economic factors are coming into play, and we know this large scale machinery could be pulled together.
Yeah, can do.
Sounds good. Yeah, I'm really happy to learn you have positive feeling and experience for this.
Yeah, no, it would be great if we can do it. The student I had who built that model is now a professor at the University of Delaware, so I'll have to bring him into the picture. But it would be wonderful. His background is computer science as well, so I think he will fit very well in with the overall group here.
Yeah, happy to extend our collaboration. I also have a postdoc at Delaware, has some interest in the climate side. Maybe there's a loop to close.
That would be great. Yeah.
Anyway, so sorry to extend this. I also have gazillions of questions. Later.
Yeah, I'm happy to set up a time and discuss with whoever is interested, because I would love to move this forward.
Yeah, I clearly sensed your passion.
Okay. Thanks very much then.
Yeah, thank you so much.
All right, thank you all so much. See you on December 16th. I think Connie is going to talk.
Yep.
Right?
Okay.
Okay.
Bye.
Bye, guys.
Thanks. So Anand, do we get enough information for the